many very important contributions. For example, even just in the heavy calculations, his works about the collective flow, hard props, strength production, and parity, and anomalous transport, and the spin polarization, and also the critical point search, are very essential for our understanding for the physics in heavy calculations. So today, we are very happy that he will tell us the chirality, magnitude, and the Coulomb plasma in heavy calculation and algebra. That's a welcome.
Okay, thank you, Shiko. Okay. It's on already? Yeah, it's on. Okay. Yeah, and I also want to thank the organizers for this summer school for inviting me to talk on something that I love to talk about, at least in recent years. So talk about chirality, magnetic field, and the quark-gluon plasma. Basically, try to give a overview of things that mostly our group has been doing. And before I started on these topics, I want to basically try to dedicate a few words to Professor TDD, who passed away earlier this month. And actually, I think that everybody knows about TD, and he was a giant in physics. And I think what most important for many Chinese physicists is that he really changed the lives for generations of physicists, and also he really changed the landscape of science in China by affecting how the science being, what kind of major facilities, how the science being done in China, and what kind of how the people get educated. And so TD is actually work in China actually has in several areas directly impact my own life. Okay, because I was a member of the Caspia program in 1983, and that program, as many of you may know, that brought about 950 young people from China at that time to top universities in the United States, and that opportunity actually opened the door for many young people who were not available to many of us. Okay, then all my career I've been working on RHIC and also RHIC star physics over the years, and of course, TD was the person that initiated the RHIC program, and also actually when we started the RHIC China collaborations on the Star China collaboration, and actually TD was really instrumental to really make that happen, and pushing both at Brookhaven and also within China to support the Chinese groups working on the Star collaboration. And also many of you know that TD and Li and Yang's work on the parity variations in weak interactions. And at a personal level, actually, we know that in standard model that the maximum parity variation was due to this neutrino properties that we only, in standard model, we only have left-handed neutrinos. And that neutrino heredity measurement, okay, actually that was Goldhaber-Grotjens and the Sonia experiment. I mean, if you don't know that experiment, you should look at it in the textbook. It's one of the most beautiful, elegant tabletop experiment that measured the neutrino heredity. And I want to mention that because I become a student of Lee Grotjens, and so again, it's kind of personally affected me that actually Lee Grotjens, actually I also learned that Lee Grotjens and TD Lee are the same. They were born in the same year, so they're same age actually. And Grotjens is still alive these days. So I then of course I, in addition to the RHIC physics, I also work on the neutrinos double beta decay experiment. So and that was an experiment try to because we know from neutrino the neutrino oscillation experiment, we know that neutrinos have mass, so therefore heredity cannot be a exact quantum number for neutrinos. So and we were hoping to that through the neutrinos double beta decay experiment we can maybe prove neutrino are Majorana particles, and maybe heredity is not exact, right? So and I also worked on this diabetic experiment. So I think in some ways, I think if you are a graduate student, perhaps back in your mind, you may, have a motivation to say, I really, admired my PhD supervisor, but at some point I want to prove that he was not quite 100% correct, right? So I was working on neutrinos. I maybe try to prove that the neutrino heredity is not exactly conserved quantum number that in the neutrinos. And but then also in heavy ion physics, I work on the chiral effect, and that of course that is a manifestation of parity variations in the strong interactions as well. So I think you can see that at least one way or another, this my research path has been really influenced by Professor Tidi's work. And also, I think many of Chinese students learning about this 系推物理系行乐合用佛明办事成. And you know the history of this. I think I was from Tufu, like a 7th century, famous point in China. So 系推物理系行乐. So at least for me, that I think try to figure out what means by 系行乐, because look at what you enjoy in life. Looks like at least TD Professor TD had his interpretations. So we try. At least I try to figure out what Professor TD's happiness on those things. And so I look at the history, that the birth of reactivity heavy ion collider. So the birth of RIC, and so that's by Robert Crease. So if you if you want to know that article, just email me. I can email the article. And so within that article, okay, and what TDD said, that I'm sure that my French colleague will enjoy that statement as well. With the Baudelaire, that you can look into the future more easily. And so I think basically doing physics and 行乐, perhaps not entirely just the physics, but something else also, the happiness. If you can mix physics, happiness, something else, then it really. So I'm quite confident that some of you will become will great achievement in the next 5-10 years, and I would be so pleased that if maybe 5 years from now or 10 years from now, our paths crossed again, you come to me and say, oh, Huang Laoshi, I think, perhaps, with a multi or something, that I could really see the physics was so clearly, and that made my discovery possible. And I hope that, that will, at least TD's remarks, has been an inspiration for, at least for myself, and I hope it will be inspiration for many of you as well. So, okay, so let me go to the physics topics. Okay, so I'm going to talk about 3 topics. Okay, one is the chiral magnetic effect, and then also talk about magnetic field in heavy ion collisions, and then talk about introduce the S-Phoenix experiment and the physics program. So, and the S-Phoenix is a new experiment at Brookhaven, RIC, and that it really has a potential to really making some significant advance in our understanding of heavy ion collisions at RIC. Okay, so the chiral magnetic effect. So I will give an introduction, introduce the chiral magnetic effect, okay, and the lessons from the previous results, and also the novel approach that we have developed recently, and I will give some results on the star measurement start looking for this chiral-magnetic effect and give you summary and some, at least some personal outlook on what we are doing for this subject. Okay, so this chiral-magnetic effect, I think some of you, during this summer school, quite a few lectures from Jing Feng and from several others talk about the chiral-magnetic effect. So I just want to point out that, and this chiral-magnetic effect, it needs the basic, couple ingredients, right? Of course, it needs a very strong magnetic field, and it needs this mu5, right? It's this mu5, and this is basically, it's a chiral current, okay? And then the coupling of this, okay, will generate this, charge separation effect. So in this part of the topological, this topological sector of this QCD, basically you can, based on what we understand of the QCD Lagrangian with the ingredients of the ground field, all those things, okay, you could have corrective ground excitations so that you can have form topological domains and with the distinct topological numbers, and the topological numbers called the Chern-Simons numbers. Okay, then the transitions between this different excited state, you can create a chirality imbalance. Okay, and the chirality imbalance, like saying that you have a different number of left-handed and right-handed quarks. Okay, and this is arising from you need to have a chiral symmetry restorations. Basically you have a massless quarks. Okay, then you will have the current, okay, introduced along the direction of the magnetic field. Okay, and that current, okay, that will lead to a charge separation in the final state, okay, around the magnetic field directions. And where the magnetic field came from, where the magnetic field come from, this is because that in heavy ion collisions, that you have participants, that those are the nucleons interacting with each other, form the core ground plasma. Then you have spectator protons, okay, and those are the protons that do not directly interact, so they were passing through each other with the speed of light. So, and when you have the spectators passing through each other, so those are the charged particles moving at the speed of light. Okay, so therefore it has a the electrical current, right? And those two currents, they're separated by the distance of several Fermi. Right? So then you can calculate the magnetic field generated by those current separated by several Fermi. Okay, so of course, given that Fermi is such a small number, so you can calculate the magnitude of the magnetic field. You find that you have a huge magnetic field. Okay, and therefore, it can lead to some, measurable effect in the experiment. And the measurable effect is the charge separations. So this kind of topological sector, okay, that's an intrinsic properties of the QCD Lagrangian. Okay, so this, I always use the analogy that this is like Einstein's general relativity. The general relativity, okay, people know for 100 years that you will predict you have gravitational waves. Okay, and people looking for it, they have good indications there must be gravitational waves, but it took 100 years until the LIGO experiment, okay, that be able to be able to really see the magnetic waves come from the merge of the black holes or neutron stars later. Right? So, so this chiral-magnetic effect, this topological effect, okay, topological effect is an intrinsic property of this QCD, okay, but it has not been observed experimentally. Okay, so, and I was very hopeful that perhaps in doing strong interactions, we didn't have to wait the 100 years to be able to say that experimentally we do see, we saw this special effect. Okay, but looks like nature has not been that kind to us yet. So we are still kind of struggling, try to find unambiguous evidence for such an effect. Okay. So the observables that we use to look at for this charge separation. Okay. Remember that we are looking for CME effect, and if there's a CME effect, it will lead to charge separation. Okay, so basically, when we look at the charge particles, the positive charge particle and negative charge particles, they will be separated, okay, along the direction of the magnetic field in heavy ion collisions in the final state. Okay, so and this is basically you form a dipole in the final state, and the dipole in the final state, okay, in strong interactions, okay, that will violate this parity symmetries. So that's what we call local parity symmetry violation in strong interactions. Okay. And so for this charge separations, okay, and we measure the basically when we measure the particles, okay, from the final state, okay, we want to decompose it, okay, decompose it into the azimuthal angle distributions, decompose into harmonic the sine cosine functions. Okay, and those sine cosine functions have a carry unique physics informations, and you learn about the flow information. We look up V1, V2 related to cosine terms, okay, the elliptical flows. So for the charge separations, we are looking at this A1 terms, that is a sine component, okay, of this angular distributions. Okay, but we cannot measure A1 by looking at average over many events directly, because when we have a nucleus collisions, okay, although you can determine the direction of magnetic field, okay, in each collisions, okay, but you don't know whether the topological charge that generated is positive charge or negative charge. Okay, so they have equal probability. So therefore, when you average over many events, then you will cancel out. Okay, so experimentally, what we're looking for is the A1 times A1, so it's A1 squared. Okay, so that component is basically looking at the charge separations, the fluctuations on the charge separations. So we will see the difference. Okay, so and this, okay, is that the quantities we use. Okay, so this is what we call gamma 112. So it's the cosine, okay, phi one particle, cosine phi the second particle, and this is with respect to the reaction planes. Okay, and sometimes experimentally we can also use the participant planes. Okay, and we need to correct for the resolution in determining the reaction plane and the partition plane anyways. So, and this gamma 112 is the quantity that we use. Okay, then in order to subtract the background, we do the opposite sign charge minus the same sign charge. So this will subtract a significant fraction of the background. Okay, then the residual background. So I will try to focus on how to subtract the residual background from this delta gamma 112s. Okay, then also we construct what we call background indicators. Okay, so this gamma 132. So the term is 1 refers to coefficient here is 1. Then the second coefficient is 3. Then this is a 2. That's 132. Okay, so you can actually expand it. You can prove that this gamma 132 is mostly background. So it does not have contributions from the CME effect. So, but it has some contributions from some intrinsic correlations in those particles in the background related to the gamma 112. So by using this background indicators, so if your method be able to remove background in this gamma 132 correlate, then it does not necessarily that you remove all the background in gamma 112, but at least you can show that your method that developed can remove the intrinsic, some of the background in the particle correlations, okay, particle correlations. So in research, okay, that people proposed, in addition to this gamma correlators, people proposed the R correlators that look at the ratio of certain particle correlations, or look at the balance functions, okay, in different ways. Okay, in the one comprehensive review particle star published, okay, that we reviewed all those different methods. Okay, you can prove that all those different methods, they are actually related to each other. Okay, related to each other. Okay, so the initial measurement, okay, in star and also in the at LHC, okay, was very exciting because we were able to, okay, measure the opposite sign gamma correlations and measure the same sign gamma correlations. Okay, then you can see that they are different. Okay, they're different. Then by subtracting the opposite sign correlations, okay, with the same sign correlations, you get what we call delta gamma correlators. Okay, delta gamma correlations. Okay, then you found that there is indeed, okay, a delta gamma signal, okay, that possibly related to this, okay, charge separations, okay, and could possibly related to the CME effect, okay. But very quickly, okay, we realized that okay, there's something additional background that we were not subtracting in this just the opposite sign minus sign background subtractions, okay. And then, okay, so in order to further understand the background, also further subtract the, to demonstrate that this correlation, okay, can be related to the magnetic field effect. Okay, so the RIC program proposed, okay, isobar collisions. Okay, isobar collisions, experimentally, it's a very good idea. Right? This is because you can, isobar means that the two nucleus have the same nucleons, but different number of protons. Okay? So because they have the same number of nucleons, so their collisional physics, okay, will be the same, but they have a different number of protons. So therefore, they will generate different magnitude of magnetic field. So if we measure the delta gamma correlations from those isobar collisions, okay, then, okay, if their contribution to those correlators due to the magnetic field difference, then you prove that you are sensitive, you have a measurement that is sensitive to magnetic field, and it's possibly related to the CME effect. CME effect. Okay, so STAR, the RIC program, dedicated 1 year RIC running to do the isobar collisions. Okay, and that is a considerable investment because RIC running for 1 year cost $160 million. Right? So so unfortunately, right, nature is more cruel than we hope. Right? So in our measurement, okay, that we did achieve our goal to reach the statistical precision of this delta gamma measurement from those isobar collisions. Okay, the isobars we used are the zirconia, okay, and the ruthenia. Okay, so they are charged, the number of protons 44 and 40. Okay, so because ruthenia has more, the 44 protons, and the ruthenia has 44 protons, and the zirconia has 40. So we expect the correlation will be larger in ruthenia. Okay, so what we found, to our surprising, was that it's opposite to what we expected. Okay, and it was quickly realized that the when we using isobars, right, the isobars have the same number of protons, same number of nucleons, different number of protons. Okay, but the way the nucleus build up, okay, you look up the shell models. Okay, you build out proton shells, you build out neutron shells for nucleus. Okay, and because the different number of protons and the neutrons, so their skin, neutron skin is different. Their shape is slightly different. So that slight shape difference in those isobars, okay, will contribute to the delta gamma correlators. Okay, so therefore, okay, those additional uncertainties, okay, makes the ratio actually below what we expected, because we expect if there's no CME effect, okay, the ratio should be 1, but it's below 1. Okay, so we can try to say take into all those different effects, okay, to bring this ratio close to 1. Okay, but then you end up with a situation that because those corrections that we all need to do, okay, will have a uncertainties, okay, a few percent levels. Okay, then what we are seeing that with the isobar data we have taken, okay, it's clearly, okay, that the CME effect, okay, is too small for us to see in those isobar collisions. Okay, so in retrospect, people may argue, say, oh yeah, I told you so, because you see that you are using isobars, Z is only 40, but the golden nucleus has 79 protons. You are down by a factor of 2, and the magnetic field is down by a factor of 2, and you're looking for effect proportional to magnetic field square. You are down by a factor of 4. Maybe we are lost some sensitivities, but I wish that I could have the drink that Professor TDD had before the running of the isobars. Then perhaps I could have seen that future more clearly at that time. But no, that's what the lesson we learned. That's the lesson we learned. So, and that later on we also learned that when we using this try to looking for the fraction of CMEs, that when you have to deal with those smaller systems, okay, that you really lose sensitivities because your reaction plan resolution, your event plan resolution also deteriorate as well, okay, compared to the larger nucleus. Okay, so we really need to focus on large systems like on gold on gold. Okay, and we need to directly suppress the background. Okay, in the isobar collisions, we are not looking at for CME signal directly. We look at the difference in the CME signal because the difference in the magnetic field, different magnetic field. Okay, so and we realize that we needed to do some event shape selections, okay, to suppress the background. Okay, so the background in the CME, okay, come from the flow-related background. Okay, that's basically the V2-related background. Then also some non-flow-related background, such as like a jet production or mini jet productions. Okay, so the flow-related background, okay, can be reduced with the selection of spherical shaped events. So if you can select the spherical shaped events, you can force the V2 close to 0. So therefore you can reduce that kind of background. Then of course, for the non-flow related background, you can reduce this by go to this low energy heavy ion collisions. You don't produce so many jets. Right? Then also you can use really forward event plans that maybe because we are looking at the middle rapidity. Okay, you determine the spectator proton event plan, then reaction plans. Then you can suppress this background. Okay. So the previously, okay, the LGC people use the event shape engineering method. Okay, in those methods, basically they choose particular region of interest, okay, group of particles region of interest like A. Okay, then you use the particle to group of particles in region B to construct the event shape observables. Okay, then use the particle region C like to reconstruct the event planes. So the particle interest, particle for event shape, and the particle for the event plane determination are completely separated from each other. Okay, so and then what they found out is that you can do some shape selections. Okay, but what you end with is that that when you try to select this Q2 to the event shape to measure the event of particle V2 for the particle interest. So although the particle region that he used to select the shape, saying that that shape should be very spherical, but when you actually go look at the particle of region of interest, you find that shape is not spherical at all. Okay, it has a very finite V2 there. So therefore, when you do that, you cannot get the V2 close to 0. So therefore, if you say, I need to have the V2 approaching 0 to remove all the background, you cannot, because you cannot get a V2 close to 0. Okay, and this is because, later on we learned that because that the V2 event by event has contributions from the eccentricity geometrical shape, but it also has contributions from the particle emission patterns. So you can start with a elliptical shape, but the particle emit does not necessarily follow exactly this elliptical shape. It has variations in the particle shape, and that part of the emission pattern fluctuations actually is very local in rapidity. So if you choose different rapidities, you don't see that correlations there. So, and that's the difference. Okay, so therefore that's that approach, this event shape engineering method was applied at the CMS experiment, also Alice experiment. Basically, you can see that no matter what you do, right, you cannot approach the V2 close to 0. Then if you are limited by statistics, if the CME effect is rather small, then you can see that when you try to extrapolate to V2 equals 0, you have a large level arms to extrapolate, and you cannot get a very precision measurement, be able to remove all the CME background, Okay, and also you don't really know precisely what the extrapolation to V2 equals 0 means. Okay, and the Alice experiment seems to did a little bit better, try to combine all kind of centralities, okay, to be able to extrapolate a little closer to 0. But then, okay, you also raise the question that if you rely on different collision centralities to extrapolate to V2 equals 0, if that extrapolation just follow the eccentricity variation based on the centrality, then extrapolating eccentricity to 0 means you extrapolate to most spherical eccentricity in most central collisions. Okay, that most central collisions only happens at almost 0 impact parameter. And if you have a 0 impact parameter, very little spectator protons to generate a magnetic field, you should expect 0 CME signal if that's the approach you take. Okay? So, and that's the struggle we have to understand this event shape engineering method. Okay, and I should mention that event shape engineering, it does select eccentricity variations. So if I want to compare my measurement with, say, hydrodynamical calculations, that works very well. But for CME analysis, we want to suppress the background from the CME analysis. Then we found that method has limitations. we cannot, okay, reliably extrapolate to V2 approaching zero spherical shape events to suppress the CME background. Okay, at the same time, that be able to say that maintain the magnetic field, okay, for the CME effect. Okay, and we did lots of simulations with the AVFD, probably from Professor Jing Feng's talk. You already know AVFD a little bit, so you'll be able to, based on hydrodynamical modeling, okay, you can introduce this chiral-magnetic effect, be able to, basically, to test your method. And we found that the standard event shape engineering method has limitations. So what we decided is that we want to do the event shape selection. Okay, I use event shape selection instead of using event shape engineering that the other paper used, because okay, if I can engineering how the collision takes place with two nucleus, I will be happy to do that, but I cannot. I can only after the collision, given whatever nature give us, then to select the shape in the final state. Okay, so we realized that, okay, I mean, actually, some people much smarter than us, I mean, realized many years ago, okay, that when we measure locally the V2 for those particles of interest, okay, that V2, event by event, has contributions from the eccentricity as well as the emission pattern fluctuations. Okay, that basically, you can have like that even eccentricity, like a source like this, but just the way the particle being emitted, you can have the events more spherical for when you taking all the particles into account in the final state. Okay, so we needed to combine those two effects so that we can select the events with a spherical shape. Okay, so with this, okay, we can choose the event shape. Okay, we also use different method as well. So basically, what we say is we want to select the events, okay, using particle of interest to determine the event shape and the V2 with the same class of particles. Okay, so the event shape variable we can use in Q2, but we can take a Q2 for single particles or Q2 for all the particle pairs. Okay, then we can also using V2 for single particle and V2 for all the particle pairs. So then with those two shape variable, these two flow observables, we can have 4 combinations. There's A, B, C, D, four combinations to make the shape selections. Okay. Then, okay, we use the simulations. Okay, again using AVFD. Okay, we can find that with the A method, okay, and with different method, basically using this A method is single particle Q2 to do the shape selections, single particle V2 to do the V2 select the calculations. Now we can also do the pair particle Q2 to do the shape selection, pair particle, single particle V2 for the V2 selections. Okay, and we found that you can, using this shape selection method to suppress the background to different extent. Okay, if we use the hydrodynamic models, okay, we found that this method C, okay, this method C, okay, we use pair particles to calculate the shape observable using single particle V2, okay, to do the projection where we get the zero background suppression, okay, suppressing the background to close to zero. So this works very well for hydrodynamical calculations. Then also we use different dynamical models, for example, like the AMPT models, okay, that we found that in this approach, we are slightly over-subtracted the background somewhat. Okay, and this is because partially that in those kind of AMPT models, okay, that the background, they are not just hydro-induced. There's some non-flow contribution background. Non-flow contribution background. Okay, and so this is so we are basically using this approach, okay, to what we call the event shape selection approach, okay, to analyze our data. Okay, so in then okay, we go back to the stars B energy scan data, and we found that's probably one of the best data we should use. And this is because using the event shape selections, in the star, this is B energy scan data, we have a event plan detect in the forward directions. Using event plan detect in the forward directions, we can suppress the non-flow background. Okay, then using the event shape selections, we can select the spherical shape particles in the final state. So we can really suppress the background. Okay, so and this is the data set that we have. Okay, with the event B energy scan data, we have quite cover the energy, okay, from 7 GeV to 27 GeV, and we be able to select to be able to suppress the background from the V2 and the background from non-flow contributions. Okay, and this is for like 19 GeV data we have, and we use the method. Okay, I already mentioned that we have basically two shape observables and two flow variables. Okay, and we can using this 4 combinations to suppress the background. Okay, and the default one that we from the hydro model is this C method. Okay, so what we found is that with the B energy scan data, okay, we want to see what's the intercept at the 0 V2. Okay, so what's the intercept at 0 V2? That's the place that we have almost a spherical shape particle emission, so that you get the minimum background for the CMEs. And if there's a residual, then perhaps there's some signal left. Okay. So we did for 19.6 GeV data for different collision centralities. So in this region is the most central collisions. Okay, for most central collisions, we have a difficulty to determine the reaction plane really accurately. Okay, so therefore the error bar is large. Okay? Then for most peripheral collisions, the V2 is quite small, so you have also large error bars. So the region, okay, that optimal for the CME search is the middle central collisions. So we use the 20 to 50 centralities, 20 to 50 centralities. Okay, and you can see that this is for the data gamma 112. The red points is before the event shape selections. Okay, then these 4 points is after the event shape selections. Okay, and this blue points are the method that in the method studies, okay, using hydro model is the best method that be able to subtract all the background in the hydrodynamical based simulations. Okay, so you can see that from the inclusive measurement to this event shape measurement, this is the magnitude of background subtraction we can achieve. Okay, so we be able to remove about 80% of the background, 80% background, and this is the fraction of this event shape signal divided by the inclusive measurement. Okay, you can see that the residual part, okay, is about 20%. So, okay, then I already mentioned that you can use the background indicate. That's the data gamma 132. Okay, we know that is entirely background, and we found that with this method, okay, we be able to remove all the background in this background simulations in the data, just as what we learned from simulations. So, and this is the data, and with this middle central regions, if we try to fit, okay, this 20 to 50% centralities, we found that there is a residual delta gamma signal, and this residual delta gamma signal, is about 3 sigma effect from 0. 3 sigma effect from 0. This is for 19.6 GeV data. 19.6 GeV data. Then we analyzed for 7 GeV to 27 GeV from B-energy scan data. And then we also went back to 200 GeV gold-on-gold collisions. We found that with this, this blue points, are the even shape selection method. You can see that at the lowest BM energies, this is very close to 0, but the error bar is large. Between say 11 GeV and 20 GeV, there seems to be a 3 sigma signal. 27 GeV, the error bar is a little large, and the 200 GeV is near 0. So that we see this, and then of course for the delta gamma 132, it's consistent to 0 over this region. So to summarize this, right, with the even shape selections, we seem to have a small residual signal in this B energy region between 10 to 20 GeV. At each individual energy is about 3 sigma. But if you say, their energy is so close enough, the B field might not be so much different, then if I combine the 3 beam energies, then it's close to 5, it's more than 5 sigma residual signals there. But if you look at 200 GeV, we don't see any residual signals. So perhaps this is a consistent with the result from isobar collisions, that 200 GeV somehow the signal is not there. Then at the lower energies, of course the error bar is larger because we don't have enough data at the lower energies. But it's also consistent with 0. So if we say that what kind of fraction of this even shape selection signals, compared to the initial inclusive signals, it's about 20% or less. 20% or less. So, and then we also will compare to what we learned from B energy scan data, previous data. Previous data, basically that we say there is a background contribution, to this delta gamma 112, and that background contribution is proportional to V2 and the data. Data is by just two particle correlations. So if we go back, that actually it was Jinfeng and Volker that proposed that we really needed to subtract this additional background coupling to this delta gamma. So they introduced the delta H correlator. With this delta H correlator, we can go back, say, with the even shape selections, I can extract what this kappa factor is. So kappa factor says that in this delta gamma correlate measurement, what fraction of this background correlate is included in this gamma 112 measurement. And what we found that looks like that kappa factor is a constant. So I hope that later on, some theoretical work will help us to understand why this is more or less constant. So let me try to summarize what we learned about even shape selection method. So with the even shape selections we have used, we were able to remove the V2 induced background. And for the B energy scan data, we were able to use the spectator protons to remove large non-flow contributions as well. So therefore, naively, we think that what the residual delta gamma 112 could be related to the charge separation signal related to the CME effect. Okay, so when we apply this method to the 200 GeV data, we saw the signal does not seem to be there. So we can put an upper limit to be less than 10%. Okay, so perhaps it's not surprising that the isobar data we took at 200 GeV, we didn't see a signal at all. So maybe even I had a drink that at that time to insist to run more gold on gold like isobars at the 200 GeV, we perhaps wouldn't see signal either. Okay. Then with the B energy scan data we have between 10 to 20 GeV, okay, at each energy, we saw a residual signal about 3 sigma, okay, and it's over 5 sigma if nature allow us to combine those 3 energies together. Okay, then of course at lower energies, okay, this approaches 0, okay, but the error bar is still large. Okay, so we need some more theoretical insights. Okay, why at 200 GeV it's 0? Okay, and also, at lower energies, it's perhaps close to 0. I mean, in many star measurement, we learned that at lower energies, say 7 GeV or below, the mat we created is not dominated with parton degree freedoms. Perhaps at that lower energies, there's no QGP formation. So therefore, maybe that could be related to the disappearance of the chiral symmetry restoration in those lower energies. Okay. Then why this intermediate, this 11 to 20 GeV, okay, why this residual signal still seem to be there? Okay. Some people actually, quite a few years ago, okay, including a paper by Dima Kazeev, they proposed that if there is a critical phenomena, okay, if you are approaching the critical region, then the topological fluctuations associated with this chirality imbalance, okay, could be enhanced because you have a longer lifetime in that regions. Okay. Then also, if I extrapolate what we learned, okay, from the RIC 200 GeV to LHC energy, then I even predict that LHC energy would have 0 CME signal as well if our method is applied. And I certainly hope our colleagues working at LHC maybe at least try it. Okay. But so far, I think all the LHC result using other method does not seem to be very promising, okay, for a possible signal. Shall we stop at here, or you want to? No, I have some more. I mean, yeah, I need probably 10, 15 minutes to finish the CME, but I can stop anyway. I did some. Okay, finish. Okay, so then the future perspective, right? So, and the people look at our method, okay, immediately say, aha, yeah, the way that you do the event shape selection, okay, could potentially bias, and it could be model dependent. Okay, so, and I agree with you 100%. Okay, this is because, like, when you say, I want to do an event shape selection to select certain class events, okay, that inevitably will have model dependence. Right? The reason for that is that when we say we want to select a shape, you are talking about a geometrical space, how the nuclear collisions that produce the participant matters distributed in geometrical space. Okay, when we do event shape selections, we do in momentum space for the final state particles. Okay, so how you connect the final state momentum distribution to relate it to the initial geometrical space nuclear distributions, that model dependent. Okay, so some hydro models can describe very well mapping this eccentricity distribution to the final state particles. Okay? But again, with the hydro kind of models, okay, our event shape selection method seemed to be work quite well, and that we proved using AVFT models. Okay, but if you say, I'm going to make a toy model to make connections between initial state geometry with final state particle, yeah, you can make a toy models to prove my method doesn't work. Okay, and I can make a toy model to prove that QCD is wrong, but that toy model does not give us any insight. Okay. So, and it appears that the event shape engineering method is more sensitive to initial collision eccentricity. Okay, and but the CME background certainly has contributions, okay, from the eccentricity related background as well as the emission pattern fluctuations. Okay, and our method was really try to combine these two so that we can minimize the background. Okay, so our data seem to show that for mid-centralities, CME search showed concentrated onto 20 to 50%, for example. So in this region, okay, in this centrality regions, if you use the event shape engineering method, you have really limited range of eccentricity variations. You cannot reach the V2 approaching 0 for long shape to minimize the background. If we try to extrapolate to V2 zero limit, that extrapolation, of course, is model dependent, and it has large uncertainties. Okay, and if the extrapolation follows the eccentricity variations, then when you insist the eccentricity to be 0, it will correspond mostly the most central collisions, then there will be no magnetic field. Okay, so and using our method, we'll be able to approach V2 0, mostly due to emission pattern fluctuations. Okay, and it appears that we have a residual charge separation signal at V2 approaches 0 limit. Okay, and how to and this, of course, approach V2 limit depends on the method, how you do the shape selections, how you do the control the V2s. Okay, with the hydro-induced background, we can show that we can minimize the background. Okay, minimize. But of course, I cannot convince everybody that our method is working for CME signal selections. So recently, actually, some people, I think I don't want to mention their name, posted a paper that saying that this method doesn't work, it just doesn't work. Okay, and they claim that they are event shape selection because they apparently favor the event shape selection method. They say that when the event shape selection method was to approach V2 limit, okay, and their method worked perfectly. Okay, and I look at their result. It's clear that the event shape selection method has a problem there. So these are the data points they showed that with the event shape method, you can see that you need to extrapolate to 0 V2. Okay, with AME, okay, you need to extrapolate to 0, 0, but you are way off from 0. You have no way to control because you extrapolate so long. You have large error bars there. Okay, then when this is the 200 GeV data, this is 27 GeV data for AMPT result. They just no way they can reliably extrapolate to V2 equals 0. Okay, then they're using different method, different models. Okay, this is using different EPOS method. Of course, again, they cannot extrapolate 0, and you can see that with this, I mean, this is way, way off. But even with this kind of data, it does not prevent them to make a conclusion that the event shape selection method works for this kind of CME analysis. I was totally puzzled. I said, no, you got to withdraw your paper because look at those figures. But they refused. Okay, so let me look. Okay, if all they want to say is there's some model dependence in the event shape selection method. I already agree with that statement. Right? So event shape selection method cannot solve all our physics problems. Okay, you need to find the best approach for your particular physics. Some physics work better with the event shape engineering. And what I'm saying is that for what we have studied, for CME search, the event shape selection we used seemed to be better. Okay, so, and then of course, people always produce their favorite toy models to prove their point, but sometimes you cannot because at least my advice is always that toy models are indeed just toys. So avoid playing, say, garbage in, garbage out games to make your points. Right? And you need to also respect the statistics. And basically, if you get a result 1 plus minus 1, okay, it's really easy for people to conclude that 1 plus 1, your result is consistent with 0. But it also consistent with anything else you want to put forward. So you need to respect the statistics. Okay, so if you get 1 plus 1, it does not necessarily mean your method working. It could just mean that your method does not have sensitivities. So I say that be critical, but also be truthful. Right? Be critical means be critical to others, but also critical to yourself as well. But be truthful is be careful what statement you made from your seat. Okay, so then also I think we still need to understand what dynamics at the RIC 200 GeV and IHC. With the event shape selection method, we found that this delta gamma 112, okay, really close to 0 at 200 GeV. And if we extrapolate to LHC energy, we extrapolate this to be very close to 0 as well. Okay, so but we know that the initial magnetic field at those energies are certainly large at t equals 0. Okay, so why we don't see the CME effect? Okay, so and we hope to have more insight. Okay, more insight. So and we want to also critical to our result in the sense that we want to ask that we see that maybe between 10 to 20 or 10 to 30 GeVs that there's a residual signals. But then we look at all the star other measurement. For example, star measured using HBT, measured R out over R side ratios. Okay, star measured V1 slopes. Okay, star measured the cumulant C2 over C2 for critical point searches. Seems to be that something deviates or something peaks or dips, okay, at this between 10 to 20 GeV. So I really want our theoretical colleagues to look at this energy regions to tell me if there's some new insight, something that we should look at more carefully on those things. Okay, so on the CME searches, okay, so we continue to need to be critical for our work. So we want to understand background contributions, okay, and we want to improve the method. So if you have a suggestion how we improve the method to suppress the background, I'm happy to discuss with you. I want to hear your suggestions. And we want to understand the magnetic field, and I certainly want to get more theoretical insight. Okay, so I will stop here on this CME searches. Thank you.
Thank you very much for the very nice lecture. I literally hear how the experimentalists can measure the interesting CME effects, and also there's a new event shape selection method there is developed. So now it's time for discussions, questions. Yeah.
Thank you very much for a very nice summary. And of course, CME is quite robust physics that we all know, what we all theorists believe. But the subtlety is, of course, the strength of the magnetic field and also the strength of a chirality imbalance or the fluctuation, right? And in that sense, I think that it is really important to understand the magnetic field effect you actually wrote here. And for this, probably I missed, but is there any the measurement of electromagnetic probes from the isobar experiment trying to see the electromagnetic effect in the very early stage of the collision, because the magnetic field effect is, of course, expected in the very early stage of the dynamics, and so the transparent probe is the most sensitive to the presence of the magnetic field.
Yeah. Thank you, Kenji. That will be the topic of afternoon lecture.
Okay, okay, thank you.
Okay, any other question? Questions from students?
I think I hope at least one lesson we learned. Also, hope everybody should be aware of that. In doing science is really you trial your best ideas, and not every idea work. And as I mentioned, that the isobar run was certainly a good idea, and the community spent $150 million for it, and we learned very useful information, tell us where to looking for it. But that particular physics objective, looking for CME, it didn't turn out to be true. To be able to really realize that kind of significant discovery that we hoped for. But there are many other physics, of course, you get from the isobar data. So this is just part of life that you aim for, like really high important scientific goal, and you hope that you climb the mountain, you reach the top, you have a moment of eureka that have discovered something, but very often you find you discover something, but not exactly what you wanted and what you aim for to begin with, and that's just a part of. Sometimes I guess I want to rephrase Professor T.D. Lee's remarks that if you have a couple you can see the future that more clearly, but also you can take that kind of setback also more easily, because you will build up your energy for your next endeavor.
Question?
The student mentioned, and so thanks for a very nice lecture. And it's not clear for me what's the difference between EISE and ESS. So what's the emission pattern? The concept behind that. You explain more?
So the event shape engineering method, is they specifically, they want to select particles in different regions to do the different goals, right? So they choose particle A region to do the particle of interest. So they use that region of particles to calculate the delta gamma. Then they use particle B, to do the event shape calculations. Then using particle C region to do the event plane calculations. So event plane calculation, we always do it separately. Then what they insist is that they're using different regions to do the V2 for the projection versus the event shape selection. So what happened there is that because that the particle A and B, the correlated part is due to the eccentricity, but the other part due to emission pattern, they are not correlated. So therefore, you selected the correlated part to do the shape selection, but the other part was still fluctuating widely. So therefore, you are in this Q2 selection, you say you approach 0 already because the emission pattern fluctuation, you say already approaches 0. But in reality, no, that part is not approaching 0 because the emission pattern, the fluctuation in the emission pattern in different rapidity regions, they are not correlated at all. They are not correlated. Okay, so what we say is that A and B should not be separated. When we say we want to select the spherical, okay, you use all the same particles, okay, but we don't want to use the same way to calculate the Q2 and the V2. So what turns out the best way is that we use the same particles. Okay, we use the same region of particles to do the shape observable calculation and the flow V2 calculation. But we're using different ways. Okay, so that the best approach is we take all the pair of particles to do the shape, then using individual particle V2 to do the control of the V2. Okay, that seems to be the best approach.
Will you give example? What's the emission pattern?
Emission pattern basically, you take the initial geometrical shape, say ellipsoid shape, whatever. Right? If you allow particle evaporate from surface, right? That particle emitted from the final state, it does not follow your initial geometrical shape. Right? It does not follow your initial geometrical shape.
So it's
it has a V2.
Two different things between the emission pattern and shape.
The emission pattern and the eccentricity induced, there are different contributions to the V2 calculation.
Thank you.
Yeah, you probably know that right before I do, but.
Okay, so another question from the students.
Thank you. Very nice talk. So in principle, the ES selection method is just about choosing out the shape variable. So it doesn't have to only see by the gamma correlation. It can also be used as up to other observables. Is that correct?
I mean, in what sense? I mean, that you want to choose your method for your particular physics goals. Like, so if you say, no, I want to select my events class, okay, to compare with some well-known hydrodynamical calculations, right? Then you ask how they do the hydrodynamic calculations. If their hydrodynamic calculation is based on eccentricity of initial geometry, then do the hydro evolution to produce final state particles. Then you only want to sensitive to the eccentricity selection. Then you don't want to use or even shape selection method because that or method is less sensitive than the other method on eccentricity selections. Okay? So that's why I'm saying that even shape selections, okay, you need to know what physics you want to do and compare to what model calculations.
Yeah. Oh, okay. I have a question. So the idea of isobar equation is that you can fix the V2 but vary the magnetic field. Before that, the star also performed the experiment of the uranium collision. In that case, the idea is that we can, for the central collision, we can fix the magnetic field, which should be zero, ideally. But the V2 can be non-zero. How is the status of the uranium collision?
Yeah, I think at least from my perspective, in retrospect, in order to really be able to understand the CME-related background, okay, it's really important that you need to tag the spectator particles so that you know what happened during those collisions. Okay? So, and what happened with the uranium collisions is that we just don't have enough precision detectors be able to tag the spectators. So you don't really know how the two ellipsoids collide with each other. So therefore, you cannot be able to, like, let's say you have two ellipsoids collide with each other. Okay. Even you can say that when the two nucleus collide with each other like this, you can have the same overlap region for the participants, but your spectator is very different when you collide like this, right? Because that part is your spectator. So therefore, you have no control of the magnetic field directions in those kind of collisions. So therefore, it's just impossible to get the CME, to be sensitive to the CME part. Okay.
Yeah, thank you. Okay, so with no further question, let's stop here and let's thank Professor Huang again for the nice lecture.
Thank you.
We'll start the second. The second lecture will be given by Professor Fukushima from the University of Tokyo. So Professor Fukushima's main research field is theoretical nuclear physics and high energy physics. He has published more than 180 papers with citation, more than 10,000. Yeah, he has many important works on, for example, Qcd phase structure, wireless conductivity, anomalous transport phenomena like ferromagnetic effect, and also neutrons, capillary stars like neutron stars, and also some Qcd effective models. I believe many of you have used the so-called polar NGM model, which was proposed by Professor Fukushima, and the ferromagnetic effect, which we heard a very nice lecture from Professor Huang, was from his seminal work, which has now initiated many discussions in our community and also in Canada's math and astrophysics. So today we are very happy to have Professor Fukushima to give us the lecture about dense Qcd method and astrophysical implementation. Okay, please.
Yeah, thank you very much for the very kind introduction and very nice invitation. And well, I'm actually working on various stuff, and I might be expected to talk about chirality and topology. But recently, I'm so much excited about astrophysical implications of our knowledge about the dense QCD matter, because this is really the important the period. I mean, the more and more data is coming from the astrophysical observation, and then, so far there was almost no experimental data strongly constraining the phase diagram, but now we have a chance to get a real constraint about the QCD phase diagram. So the paradigm shift is actually happening now. And so here is my lecture plan. The first part is actually the one I gave in the morning, and then I will continue the advanced one in the afternoon. But the basic one is actually the foundation of nuclear physics and also the neutron stars. So this is really the very introductory part for students. So you must not hesitate to ask any question to me. So you can always interrupt me. Okay. And advanced course is a little bit, but not so much advanced, but a little bit advanced the ideas about the, especially the continuity of the phases from nuclear matter to quark matter, and also some application to the gravitational wave signals. So this is the plan. Okay, now let me begin with a very, very basic part. That is the foundation of nuclear physics. That is mostly the textbook knowledge. So to most of you, this is something you must already know. Well, here is the basic, the numbers, some of the basic numbers you must keep in mind. That is actually the saturation density. This is the most important number you must memorize. Okay, and so that is, if you see the density of the nucleons or in heavy nuclei, that is actually known to be saturated to the value around 0.16 nucleon per cubic femtometer. And this density is called the normal nuclear density or saturation density in nuclear physics. But in astrophysics, usually the people use a little bit different unit that is called rest mass density in terms of gram and centimeters. So then in this funny unit, this is actually really a gigantic number, like 10 to the 14th. Anyway, so this is a number. Okay, so you don't have to memorize this, but you should memorize this number. Okay, this is most important. And then, so you must develop a feeling how dense or how dilute this number is. And for this purpose, I want to introduce the concept of a percolation. Okay. That is, if you consider the nuclear size, the typical nuclear size in this way of some region in which the baryon number is localized, that is some central core of the baryon,
And also that is surrounded by the interaction cloud. That is a pion, right? The pion mediates the interaction. So this soft scale, this interaction scale is typically given by the pion mass, 1 over twice of the pion mass. That is a 0.7 half femtometer. This is actually some interaction range, okay? The typical interaction range. And if you make some theoretical computation, you can show that the baryon number is localized in more the compact region. That is around 0.5 femtometer. So this is a hard scale. And then if you compute the closest, the packed state, that is some, what was the name? The FCC, the phased, the centered, I forgot. Anyway, okay, the most, most packed state, right? You must know better. But anyway, the filling rate is, in this case, 74%. That is quite well known, right? And then if you actually make the closest, the packed state, using this hard scale, the shorter one, okay? And then you can estimate the average number of the baryons you can find in some cubic. And then you see in this case, the highest density you can achieve is 1.4 over nucleon over the per cubic femtometer. So this is actually, as compared to this saturation density, the almost 8 times the saturation density. So this is actually, if you want to keep the shape of a nucleon, then this is the highest density. And if you go beyond this density, you must break the conventional picture of nuclear physics. So the nuclear matter does not exist beyond this point, okay, the highest density. And in fact, if you see the deep inside of a neutron star, this is exactly the density you may expect. So it is quite natural to have some kind of a transition to more fundamental degrees of freedom. That is quark matter. Then the question is how you can get quark matter from nuclear matter. This is actually the central question many theorists are working on. Anyway, so this is, and also, this is not really the population, but such, the closest packed state. But what is percolation? What is percolation is, okay, if you randomly put the particles, okay, this is just the cartoon I took from Wikipedia. But if you are interested, I recommend you to visit the Wikipedia description of a percolation. It is really a technical, and so it actually describes all the details like a textbook. So this is actually the most complete description about percolation theory. But anyway, so I took this cartoon from Wikipedia, and the idea is, okay, so here you assume that each particle have some size, okay, and then you put randomly put the particles on the space, and then if there is any overlap between them, then so this is a closed, the connected, and then the connected domain should develop once if the density is increased more and more, and eventually some connected paths can be built if the density is larger than some critical density. Okay, and then you can actually compute numerically simulate this kind of phenomena. And in the case of a 3D case, 3D population case, then you can see that the critical filling density is 34%. Okay, this is okay, so very different from this one. Okay, this is the closest packed one, but only 34% is enough to achieve such population transition. And then if you use this soft scale, okay, the soft scale, the interaction the cloud range, then you can actually estimate also the typical density, that is 0.24 nucleon per cubic centimeter. That is actually 1.5 times the saturation density. So this is actually the typical density where some interaction network is expected. And once the interaction network is built, then the many body interaction must be taken into account, and that is already beyond our common wisdom of nuclear physics. So our nuclear physics, the technique breaks down already at this density. So this is not a large density, but not surprisingly, the conventional method like a chiral AFT or anyway, many body techniques, calculations may break down already at this density. And that is already indicated by astrophysical observation. This is a very interesting point. I'm actually coming to this point later. But anyway, so this is quite interesting. Okay, so these are the typical numbers used to keep in mind. Okay. And then the phase diagram. If you see the typical phase diagram, this is actually one of the most well-known phase diagrams that appeared in the long-range plan in nuclear science in the United States. And then you see the typical density region is 1.5 to 8 times the saturation density. And if you express this density in terms of kilogram and the cubic centimeter, this is actually the typical scale is a trillion kilogram per centimeter. This is really the very high density, right? And also, if you see the temperature direction, the critical temperature is around the Qcd scale, the lambda Qcd scale, that is 200 MeV. And if you express this in terms of our daily unit, Kelvin, then that is a trillion Kelvin. So my favorite phrase to describe Qcd phase diagram is that, so this is actually a trillion physics. Okay? So such very extreme physics. Okay? So anyway, this is a typical scale, okay? And then there are also several important numbers you better keep in mind. That is actually, as I told you, the saturation density is of course known, but if you express that in terms of the energy density, then because the nuclear mass is expressed in terms of the MeV, the 940 almost, and so the saturation density or the energy density corresponds to roughly the 150 MeV per cubic femtometer. So this is a very important number. Okay, so please keep in mind this number. Okay. In later discussions, I will actually refer to this kind of the number for reference. And anyway, the important point is if you see the latest lattice Qcd simulation, that is possible along the temperature direction. Not really the density direction, but this is just the temperature direction. But then you see the tremendous change in terms of the degrees of freedom that is measured by a dimensionless quantity, that is a pressure divided by T to the force. And then you see, so this increasing behavior is related to the liberation of the color degrees of freedom. So this is the confinement. And then it happens in this relatively narrow temperature region. And that is actually this. So here, if you compute the corresponding energy density, that is 200 to 500 MeV to a cubic femtometer. So this is actually the 1.5 to 4 times this saturation energy density, okay? So this is energy density where you can expect some change from the confined object to a deconfined object, okay? So this is quite, this is established fact, by the way, okay? Okay, and in fact, if you see the phase diagram, there are more and more structures. And as I told you, we are interested in this energy range. Oh, sorry, not n, but epsilon, sorry. So this is the typo. N is actually only the density, but energy density, sorry, the energy density. And in this case, this is around 4 times energy, saturation energy density. And so in the density axis, we can access up to probably the 8 times the saturation energy density, in which you might expect some color superconducting phases or some exotic phase called the coconic matter. I will explain what it is later. Yeah, in fact, actually, recently I made a contribution to a big volume over 50 years of Qcd. And in fact, last year was the 50 years anniversary from the birth of Qcd, the quantum chrome dynamics. And then there were several events, and then as a part of that, there was actually the big volume published and with many co-authors, and I was actually one of them. And my contribution can be found in chapter 7 about dense QCD. And this is actually very pedagogical introductory section. So the other part, rather technical, I must say. But anyway, my part is very readable. So okay, so you can have entertainment. So anyway. Okay, now let me explain. Oh, by the way, if you have any questions, so as I told you, please stop me anytime. Okay. Well, but to understand this phase diagram, so here I have actually the line here and also line here. But to explain this, this line, let me start with this more conventional line. So this is the nuclear liquid gas phase transition part. Okay. So by the way, this is a fact. Okay, this liquid gas phase transition is a fact. But all these fine structures, they are all theoretical conjectures. Okay, no experimental evidence. So it is so in that sense quite reasonable to start with a fact, right? Fact part. The fact part is a nuclear liquid gas transition, and so here is a cartoon. The cartoon of the energy per particle, the energy per the atomic number. And then you see, so this is a typical the behavior you can find from any nuclear physics textbook. And then you see that saturation density corresponds to this most stable density. Okay, and this is the reason why you can expect such as a saturation behavior of a nuclei. And so the important point is this symmetric nuclear matter is a self-bound system, and any self-bound fermionic systems have a preferred density, and then the diluteness is realized as a mixed phase. Okay, and so this is how we can live. Okay, this is how we can exist. Otherwise, to achieve some kind of the baryon density, if the system is uniform and completely thermalized, then of course our existence can be is just diluted away, right? And so we live exactly on this point. Okay, we live exactly on this point in the mixed phase. Okay. And so this behavior, this behavior of the single particle energy is related to the phase transition in such a way that if you take this derivative, and then the derivative, the vanishing means that you have some the extrema here, right? And so typically the minimum of this the behavior. And then if you compute this, and if you use thermodynamic relation, then you can prove that this is actually nothing but the condition that the pressure of two phases are equated. And that is a condition to have the first order phase transition, right? And so the existence of this is related to the first order phase transition. So, this saturation behavior is of course related to the this first order phase boundary in the chemical potential plane, okay? And but this argument also implies that even in the metastable case like this, okay, in this case, of course, the most the stable state is found at zero density. But so here, so this is only a metastable, and this is not the case for nuclear matter. But this is typically the case for many the Cork-based the model calculations, like number-ionization model at finite density. And this is the reason why you can find the first order phase transition on the phase diagram here. Okay. So in this sense, the physics is quite similar. Okay, so this physics and many people say that this is a chiral phase transition become first order, but actually this is nothing but the phase transition in terms of the density, and so the underlying mechanism is just the same, but the small difference is whether this is absolute minimum or this is a metastable state. Okay. So this is how you get such a phase diagram, but of course everything is model dependent, and so there might be the no metastable state depending on the model parameter, and also the location or the existence of the first order phase boundary on the phase diagram is not really completely fixed.
This is only at 0 temperature.
Yeah. So Yes. This is the argument for the zero temperature only. Yeah. Okay. Okay. Then what is this depth of the potential? Okay. What is this depth? Okay. This depth is known to be 16 MeV, and how we know that? And we know that from the the phenomenological mass formula, the Weizsäcker-Bate formula, the mass formula. And so you can actually express the mass of the nucleus in this way. That is the sum of the nuclear mass. The A is the atomic number, and just forget about the mass difference between proton and neutron. And then roughly, this gives you the bulk part of the mass, right? But of course, this is a bound system, and so the binding energy must be subtracted. Okay. Then the question is how the binding energy is given. Then the binding energy has several different components. One is a volume term and surface term and Coulomb term and symmetry energy, symmetry part. So that is, the volume part is, if you have some attractive force between them, then of course your volume term is expected. But of course, the surface part is overestimated, and so this must be subtracted. This is the reason why this is minus. And if you have many protons, then the Coulomb repulsion is cost energy, and then the binding energy has minus contribution from Coulomb repulsion, right? And also, the symmetry energy means that if you have a different number of proton and neutron, then the Fermi energy difference is enhanced, and it costs also the energy. And so, so this is the term that is responsible to achieving the nuclei having almost the same number of protons as the neutrons. But oh yes, and then if you consider the symmetric nuclear matter, that is actually the proton number and the neutron number are the same. And if you take the thermodynamic limit, the atomic number going to infinity, then only the volume term remains, right? So this is the dominant part. And then this coefficient AV is known to be a 60 MeV. This is how you get the binding energy of a nuclear matter, okay? And so this is actually a quite a useful formula. This is very simple, but very useful to understand many things. Like, for example, as I told you, for small atomic number, the symmetric energy makes almost the same number of protons and the neutrons. But because of this Coulomb repulsion, the Coulomb energy, if the atomic number becomes very large, then the proton, the neutron is more dominant than protons. Okay? The neutron is more favored, and then the beta decay makes proton into neutrons. And if the atomic number is too large, okay, then the heavy nuclei break up into the smaller nuclei, and that is a nuclear fission, right? And that threshold can be also computed using this formula, very simple formula. And if you see the nuclear chart, okay, so this black one is actually a stable nuclei, and then so this stable nuclei, this line can be actually computed very easily, computed using this binding energy, okay? And then if you see, so this horizontal axis is a neutron number, and this is a proton number. And if there's the same number, then the slope is 1, right? But if you go to a heavier and heavier element, then the neutron number is more than a proton number. And this is actually understood from this very simple formula, okay? But in fact, the neutron star is actually the very different the matter from the matter you can create from the heavy ion collision, in the sense that, as I told you, the symmetric nuclear matter means that the proton number and the neutron number are the same. Okay? And then you can introduce this parameter delta. That is a ratio between the difference between the proton number and the neutron number. And if this delta parameter is 1, this is actually purely neutron matter. And in neutron star, because of the Coulomb force, the purely neutron matter is approximately the matter you can expect in the deep cores of a neutron star. And so, actually, if you see the symmetric nuclear matter property, you can actually find the saturation point. Okay, so this is actually the energy per particle. And then, as I told you, so here is actually where you can have the first order phase transition and the stability point, the saturation density here. But if you see the pure neutron matter as a function of the density, there is no such stable point. And so, in this way, actually, if you consider the neutron star environment, the phase diagram is actually changed. Okay, so this is gone, this structure is gone, and probably the chiral property might be also affected by the very different isospin contents. Okay. Now actually, let me give you a quiz. Okay, so this is in fact, so you can find this quiz. The last year, the international the physics Olympia that was held in Tokyo, and please don't ask me who made this question. But okay, this is a very good quiz to understand how the neutron star can exist. Okay, the quiz is this is actually the second problem of this. Okay, so you can actually download the whole theoretical exam here. Okay, from here. But anyway, so the question this quiz is, okay, as I told you, if the atomic number is very large, the system is unstable, okay? It makes the nuclear fission. But if it is really, really big, then the gravity can stabilize this gigantic nuclei, okay? And so let's estimate how many atomic number you need for stability. And for this purpose, you can actually include the binding energy coming from the gravity. Okay, that is of course given by gm squared over r, right? So this is just the formula for the gravitational energy. Yes, and then what is this r? Okay, in nuclear physics, it is known that the nuclear radius is proportional to the atomic number to the power of 1/3. Okay, with some coefficient that is known to be a 1.1 times a femtometer. Okay, and then let's estimate this condition. Okay, the total binding energy is A is very large, so you can just forget about the other terms, the surface term, and also let's assume the neutral that this is a pure neutron matter. Okay, and then the Coulomb term is also dropped, and then what is remaining is only the volume term and the symmetry energy. Okay, the symmetry term. So this is actually the binding energy, but this is negative. Okay, the H sim is larger than V. Okay, and so this is of course unstable. Okay, the binding energy is not positive but negative. But you can add the gravitational part. Okay, the gravitational part is this. And in fact, this the atomic number dependence is to the power of the 5/3. That is actually estimated from this formula, and the total mass is of course proportional to the atomic number times the nucleon mass. Okay, just forget about the binding energy. That is a very small contribution. And the radius r is given by this formula. Okay, this is a 1.2. Okay, sorry, I actually have made a mistake. Okay, this is 1.1, but okay, for this estimate I made a mistake. But anyway, so this is not really a big difference, but 7 times so this blah blah. Okay, so this is such a small number. Why? Because here you see the gravitational constant here, and the gravitational constant is related to the Planck mass in such a way. Okay, so this is essentially the Planck mass, the inverse Planck mass squared. So the gravitational constant is so small, that is the reason why the Planck mass is so huge. Okay, and so this coefficient is such suppressed by the gigantic Planck mass. Okay, but anyway, if the atomic number is large enough, okay, this gravitational part overcomes. And of course, we already know that the volume part A and the symmetry energy, and also, so, okay, this is a theoretical estimate for this gravitational part, and so we can actually get the critical value of the atomic number, and that is actually given by this, and so this is really the gigantic number like 10 to 55. And from this, actually, you can estimate the radius using this formula again, and then the size is 4 kilometers. Okay? So this is actually how you can understand neutron star as a gigantic nucleus. Okay, the nucleus. Okay, one single gigantic nucleus can be stabilized in such a way, and then the typical size is actually a kilometer, and this is actually correct order. Okay, order of magnitude estimate is correct, surprisingly. Okay. Okay, so now let me come to the foundations of neutron stars. Okay, now the neutron star was theorized by Lev Landau in the year of 19. Oh, by the way, so if you have any question, I think that everything is so basic, and so I guess that everything is very clear to all of you. But if you have any question, of course, you can stop me anytime.
Exercise.
Yeah.
If you replace nuclear matter by dark matter, can you also estimate a radius of the dark matter? Stable dark matter.
Yeah, but in that case, there is no saturation property known, and then how I have no idea how can I estimate the radius. So this radius estimation comes from the saturation property. I don't think there is any saturation property for a quark matter. But I don't know, it depends on the existence of the stability or the, okay. Of course, yes.
There must be.
Yeah, okay. You can compare to the single energy, and then, yes, but it is model dependent, I must say.
Protons and electrons, no? Protons and electrons are unavoidable, the neutron star. Protons and electrons are unavoidable.
Yeah.
As soon as you have the neutrons, I mean, there will be decay. And then you get a certain fraction of protons and the corresponding electrons also.
Yeah, sure. That I neglected for simplicity. This is just the order of magnitude estimate. Okay. Okay, and now the neutron star part. The neutron star was theorized, and his paper was published in the year of 1932. And so people actually believe that some people actually think that, oh, Chadwick's paper, Chadwick's discovery of neutrons was reported in January 1932. So some people say that the Landau get the idea of a neutron star according to the discovery of neutrons, but this is actually not the case. So that theoretical consideration was summarized in this very nice article. And I had actually some discussion with Gordon Bem. So Gordon is still very, very active. And anyway, this story is quite interesting. If you are interested in this theory, the history, then it is very nice. So this is really a nice review and consideration about the history of the theory. Anyway, the conclusion is his first draft was actually completed even before the discovery of neutrons. And so he just considered that if the density is very high enough, then the protons and electrons must make somehow a composite, neutral composite. Of course, that is nothing but the neutrons, but even without knowing neutrons, he actually conjectured the existence of such the stellar object. Okay? So this is actually the strength of theory. Okay? This is the strength of imagination. Okay? Even before discovery of something, you can actually make the theoretical conjecture. So this is really a good story. I like this story very much. Anyway, to understand this, the force balance equation is the most basic equation. That is, if you consider the balance equation between the infalling force and outgoing force, of course, the infalling force is a gravitational force, right? But if you have the pressure gradient, of course, the pressure is higher inside of the neutron star. If you go to deeper and deeper inside of the neutron star, the pressure is greater. And this means that this surface element inside of the neutron star receives some force coming from the inside to outside, right? And so that is actually this pressure derivative, pressure gradient. And so they must be balanced. And then this equation must be coupled to this the mass equation. Okay, if the energy density is integrated, then you can get the mass enclosed at the point of the radius the r from the center of this star. So this is the Newtonian the equations. So this is a very simplified version. But of course, for reality, you must solve a general relativistic the equation that is called the Tolman-Oppenheimer-Volkoff equation. But the structure is just the same. Okay, so you have some relativistic, general relativistic the corrections like here and here and here. But if you take the speed of the light or infinity limit, then these terms are actually gone, and then it simply reduces to the non-relativistic equation. Okay, so it is quite natural extension and simple extension from this Newtonian gravity, right? And then what you should solve is actually you should integrate this equation coupled with the mass equation, but one information is still missing. That is a relation between the energy density and pressure. Okay? This capital M is given by the previous relation from the given from the energy density, but this is not yet closed, and so you must need some relation between P and epsilon. Okay? Otherwise, this cannot be solved. But once it is given, that is called the equation of state (EOS). Okay, once this is given, the machinery is you can just start solving this the differential equation with the initial condition. That is R equals 0 at R equals 0. That is the center of the star. The density is the highest, right? So okay, let's parameterize that the largest density, the energy density epsilon c, the central energy density. Okay, of course, it depends on the star. Okay, the many different stars may have different values. Okay, and so this is just a free parameter. Okay, simply determined by the observation. And then from EOS, the corresponding pressure is determined. Okay, and so once this is fixed, then you can actually integrate this. This is just a very simple, differential equation, and up to the point where the pressure is 0. Okay, the pressure equals 0 means you reach the surface. Okay, and so this defines the star size, capital R. And then you can actually integrate the mass from 0 to capital R to get the total mass of the star. Okay, in this way, as a function of this central density epsilon c, you can get M and R. Okay, this is the machinery. By the way, this is again the quiz I made for the International Physics Olympia in Tokyo. But in fact, the problem part was too lengthy, and then it was actually eventually cut. And so if you visit to the official page, then you cannot find this problem. Okay, so but I'm so proud of this very instructive the quiz. So okay, let me just explain what I wanted to ask to the student. That is, just assume the equation of state the polytropic EOS. This is the simplest one of the simplest one. That is now the pressure. Okay, sorry, the notation was a little bit changed, but the pressure, capital P is the pressure, and then the rho is the mass density. Or the energy density or whatever. Anyway, the rho, and then to the power 1 plus 1 over n. Okay, the n depends on whether you consider the relativistic gas or non-relativistic gas. Okay, this is the equation of state parameterized by one parameter, that is n. Okay, and then so this is the simplest is the equation of state, and this is called the polytropic form. Okay, so this is a quite common form that many people adopt in the astrophysics. And then you can actually use this and equation 2 and okay, the 3 and okay, so here I put actually the equation number 2 and 3. Okay, so you can eliminate the m and okay, you can get actually the single differential equation by eliminating equation, okay, the 2, 4, and 3, and then eventually you can get a very simple the second differential equation like this. What is psi? Okay, the psi is actually psi to the nth power is rho over rho 0. Rho 0 is rho 0 is the central density. Okay, corresponding to this. Okay, this one. And then also the R is also rescaled by some free parameter R0, and Guzai is dimensionless the radius. Okay, and then this is such a very simple equation, the differential equation, right? And this is called the Lane-Emden equation. And so the general structure of this differential equation is very well understood. That is, okay, so this is the final form, okay? This is the final form. Psi is, this is a proxy of the density distribution, and the Xi is a proxy of radius, okay? The dimensionless variable. And then you see that the solution as a function of this n, parameter n, then you can see this behavior, okay? This cycle 1 means, okay, this is the density is actually equal to the central density, so this is actually the center of the star, okay? And from the center of the star, if you go to a larger and larger radius, then you hit eventually 0. And so this, the point 0 is actually the radius of the star. Okay? And so if n is small, the radius small, and if n is large, then the radius large. Okay? So this is the behavior. And interestingly, very interestingly, you can compute the mass. Okay? From this actually, well, okay, just using with one parameter, that is a derivative. Derivative at this point to cut 0. Okay? This is denoted by this psi prime. Okay? But this, with this one parameter psi prime, you can compute the mass, total mass of the star. This is amazing. Okay, this is a beautiful calculation. Okay, this is miraculous, right? Anyway, okay, using this property of the differential equation, you can integrate. You can actually make the very, simply integrate. So this integration, this integration is analytically done. Okay, in a very easy way. Okay, this is really amazing. Anyway, so in this way, the mass can be expressed, and then actually the mass, the dependence of the mass to the central density can be analytically obtained in such a way. Okay, and then this expression is so interesting. Why? Because, okay, n equals 3 corresponds to the relativistic equation of state. Okay, if you have a very dense limit, then the relativistic EOS is expected, right? And then n equals 3 is expected. But what happens? What happens there? Okay, there is no rho zero dependence, right? For whatever heavy object, the mass, okay, the dense object, sorry, for whatever, okay, for any large value of the central density, the total mass does not change. This is really funny, but anyway, this is the conclusion. So this is actually derivation of the Chandrasekhar limit, okay? So in such a way, you can actually prove that there is actually the upper mass limit of the white dwarf star. And then the Landau actually considered what should happen if you go beyond such a Chandrasekhar limit. Okay, so he actually himself derived such a Chandrasekhar limit independently from Chandrasekhar. And then he considered what happens if the object is heavier than this mass limit. Okay. But so this is a little bit complicated story, but there is actually an even simpler way to understand the stability of a neutron star. So this is actually my favorite very simple argument. That is, okay, just consider the very relativistic system. Okay, the very relativistic system, the typical momentum is just given by the density to the 1/3, right? To the 1/3. And then the kinetic energy is simply given by the momentum times the speed of light and the number of particles. Okay, this is the kinetic energy estimate. And because the density is given by the particle number divided by the volume is r to the cubic, and so this is typically proportional to this, right? This is just a parametric dependence. Okay, I didn't care about the coefficient, but okay, so. You get so this A dependence and R dependence from this very simple expression, right? Then you can actually get the total energy. That is the sum of the kinetic energy. That is this one, and the gravitational energy. Okay, like here. And then the question is if if you want to optimize the size of the object, the capital R, if this is positive, then the R going to the infinity is stable. And if this coefficient is negative, then R going to 0 is the more lower energy, right? So this means that if A is too large, okay, this second term, gravitational term, has a stronger A dependence. And so if the atomic number is too large, this gravitational one is too dominant, and then this makes that this total energy becomes smaller, negative smaller and smaller for smaller and smaller capital R. So eventually the R goes to 0 and the system collapses into the black hole, right? And then, the A value must be the critical value, right? For the stability of the object. And of course, you might think that, oh, even when this is positive, the R should go to infinity, and so in both sides, the system must be unstable. But don't worry, because if R becomes infinitely large, then the system becomes more and more dilute, and then the system is no longer relativistic, but the non-relativistic formula must be used, and then the kinetic energy should be proportional to 1 over R squared. And then so this one is anyway the suppressed, okay? And then eventually this overcomes. In such a way, there is some stable point is expected. Anyway, from this consideration, you can actually expect some upper mass leaping. Okay? If A is too large, okay, the system is unstable and collapsing into the black hole or some R equals 0 object. Okay? And so what is this critical value of the atomic mass of the critical mass? That is actually simply estimated in such a way. And from this estimate, again, the Planck mass appears here. Anyway, this is a beautiful formula. Of course, not exact because I forgot about, I didn't care about the coefficient. But anyway, from this formula, you can get twice over solar mass. Okay, and miraculously, this is actually very close to the upper mass of the neutron star that you can see from the observation. So this is the compilation.
Yeah.
Yeah, okay.
In the previous slides, I think this is a very nice argument, which is for 3 spatial dimensions. Supposedly,
Yes.
live in 2 spatial dimensions. I think maybe the first term will be A squared, capital A squared.
Okay.
There will be no black hole.
Oh, but then the R dependence is also changed, right?
I think the first term is just R.
R dependence also comes from so here, and this is 1 over D, right?
Yeah. The volume is R to the D. So
yes, you are right. I see. Okay, interesting.
Is that true that 2 dimensions there's no black hole?
Of course, this argument is too naive and nothing to do with the black hole itself, but simply this is the stability of. Okay, but it is a very interesting question. Okay, but I don't know the answer. Sorry. And if any student have any question, please stop me. Huh? Well, so here is actually the compilation of the observed data, and so here, so this region is actually the 68% credible region. That is 1 sigma, and so most of these regions comes from the X-ray spectrum. And but there are several exceptions like this. Okay, so here the mass is very strongly constrained, and so here, so this data is from NICER experiment, and also so this one is actually from a gravitational wave, GW70OA17, that I will explain later. But actually, this measurement, okay, why this measurement is so exceptionally strong to constrain the mass, only mass. So this is extremely interesting story. Okay. So this is again my problem. That this is actually the International Physics Olympia is of course Olympia for high school students. So that you can have some entertainment. Okay, you must be better than high school student, right? So you must solve everything. Okay, so this is actually includes the derivation of a Shapiro time delay. Shapiro time delay is what is this? So this is actually the general relativistic effect of the time delay. Okay. So if you have the gravitational potential, the time is delayed, and then the effective speed of light is changed, and then from that you can actually compute some time delay, for example. So this is a very simple geometry. Okay, so here you see the neutron star, and consider the binary system of a neutron star and white dwarf. Okay, and then neutron star is mostly the pulsars, and you get some electromagnetic signal from the neutron star. With a very exact timing, and then because the signal comes very close to the white dwarf, and so the signal receives some time delay effect coming from the gravitational potential from the white dwarf, and then on the Earth we observe this, and in such a way, so we can measure the time delay, and then you see if. Okay, this is binary system, the schematic picture of the binary system, and if the geometrical structure is like this, okay, so here is a neutron star with a pulsar, and this is a white dwarf, and if, okay, the geometrical structure happens to be like this, then of course the time delay is maximum, right? But if you wait several days, then the geometry, okay, the configuration is changed like this, and then there's almost no time delay effect, right? And in such a way, if you see the time delay as a function of time or days, then there's a maximum delay and a minimum delay. And from this difference, you can estimate the strength of the gravitational potential, and from which you can actually estimate the white dwarf mass very, very precisely. Okay? And from this, the geometrical structure of this binary system, the counterpart of the binary system is also known. And so in such a way, the neutron star mass is very precisely determined. This is really a beautiful measurement and really interesting. And also the derivation of this formula is also quite easy. So just download the problem I made. Okay. Anyway. And so this is the very famous paper, and this is actually the data. And you see this red point, okay, the very small one. This is a pulsar, and this blue one is a white dwarf. The white dwarf is 1,000 times larger object than neutron star. The mass is comparable, okay, up to the 1.5, 1.4 solar mass, but the size is very different. So very dilute object. But anyway, still the gravitational potential is large, and then the time delay is seen in such a beautiful way. Okay, from this, the mass was estimated like almost 2 times the solar mass. Okay, and then you see that if the equation of state is not hard enough, stiff enough, then all such equation of state, some theoretical models are completely excluded. Okay. So this is really a very, very strong constraint, and so people are really surprised. Okay, so in the year of 2010, many people are really shocked. Okay, so this is really a beautiful experiment, and really the game changer. It was a game changer. Well, so in such a way, so this strong constraint comes. And also, I must mention that recently the NISA measurement, NISA is the timing measurement. Okay, I didn't prepare the slide to explain the idea, but the idea is very simple. That is, the pulsar is rotating, and the light comes from the hot spot, and the hot spot is rotating, and so if the hot spot goes behind, then you cannot see the light. But still, because of the gravitational lensing effect, you can actually see the light. Okay, and so from that you can estimate the strength of the gravitational field surrounding the star, right? But of course, it depends also on the radius, right? So if the radius is very large, or if the gravitational force is very large, then they actually look like the similar effect. And that is the reason why the uncertainty band extends like this, okay? The larger radius and the stronger gravitational field. Anyway, the data is more and more data coming, and so this is really exciting development. And the idea is, okay, once such neutron star, the mass and radius distribution is known, okay, then you can actually reconstruct the equation of state. That is, okay, mathematically it was proven by Lindblom that this relation, the equation of state and mass radius relation, 1-to-1 correspondence, even in the case with first order phase transition. it is not okay. At first, it might be a very strong and surprising statement, but you see that even with the first order phase transition, there is actually no jump. Okay, what you see is actually the plateau like this. Okay, the pressure never ever has a discontinuous jump. Okay, but only the energy density. Okay, the pressure is always continuous, and so with this kind of equation of state, you can one-to-one correspondence. So you can actually, in principle, find the first order phase transition from the information of the mass radius distribution of the neutron star. So this is the idea. And then the people actually say, quite often say that, equation of state is stiff, or equation of state is soft. And so, so there's actually the convention that the equation of state is called stiff if the pressure is large for the fixed energy density. Okay? Or the people say that, this equation of state is too soft if the pressure is small, if the energy density is fixed for the same energy density. If pressure is smaller, then that the equation of state is called softer. Okay? This is our convention. Okay? And so this means that actually the speed of sound is nothing but a derivative of the pressure with respect to the energy density. And so the stiff EOS means that the speed of sound is larger. Okay, if you have some enhancement of the speed of sound, then that is a signal to have a stiff EOS and vice versa. Okay, so you should keep in mind, okay, so this correspondence. But there is actually one confusing point. That is, of course, we QCD people are used to the representation of the pressure as a function of the chemical potential. But in this case, actually, the correspondence is a little bit tricky because, okay, if you have, for example, the pressure, the behavior as a function of increasing chemical potential, and then how to read the energy density, okay, for fixed value of the pressure. The energy density is given by this formula, okay, and this formula means mu times this derivative means the extrapolation from this point to this, the crossing point of this, right? And so the intercept of this. And so, okay, and so of course the sign is flipped, but anyway, so this means that if the energy density is larger for the same value of the pressure, of course, this is softer, okay? So this means that if you find such pressure actually going above, the steeper and steeper like this, then that is softer equation of state, okay? So this correspondence is completely different, okay? So you should be very careful. What is plotted against what? Okay, and so if this is energy density, then if you find the pressure curve above, then this is stiff. But that situation is completely the other way around if the representation is in terms of the chemical potential. Okay, this is a very confusing point. Anyway, so this fact, so you can understand also from this very compact formula. So this is a very nice formula I want to introduce, but anyway, this is a very technical point. So if you want to do some concrete research, this is anyway very, very useful formula to represent the pressure as a function of the chemical potential from the given data of the speed of sound. Anyway, and finally, let me make a remark about the PQCD calculation. Of course, in PQCD, the people computed the pressure as a function of the chemical potential. And if you see in the massless case, of course, the leading order gives some coefficients times the mu to the fourth power, right? And as long as you have this behavior, the energy density is always 1/3 of the pressure, okay? So you can just confirm this using the thermodynamic relation. And the next order, okay, the next leading order, usually, of course, you have alpha S correction. But alpha S correction, but of course, as long as this theory is a massless one, of course, what you have is something times the mu to the fourth, okay? The coefficient is changed. This has actually alpha S correction. But if you see that as long as the astrophysical equation of state is concerned, there is no change, okay? Even with PQCD correction, there is no change. But so this is simply conformal, okay? And so in this sense, you must go to next leading order to see some correction from QCD to the equation of state. This is also a very, very confusing point. Okay, and at this order or next to next reading order, you have actually a log collection, and this log is resummed into the form of the running coupling constant, and this is actually the dimensional transmutation, and some mass dimension is introduced by this. And in this way, the conformality is broken, and scale invariance is broken, and then some new scale must be introduced. Okay, so this is actually how PQCD works for astrophysics. Okay, now I think so. This is as I promised, the end of the basic course, and so I think so. This is the exact time to stop here. And so, if you have any question, I'm very happy to answer.
Thank you very much for the very nice lecture. It's very inspiring. So, any question?
You mentioned this one-to-one predominant between POS and mass.
Mm-hmm.
That's the only concerns that we have given the first order phase transition. What happens if you consider some further like color superconducting phase? Do you think that change?
Yeah, so even with the color superconducting phase, the first order phase transition or second order phase transition, or so such a structure could be introduced. But this argument is not changed. But there is actually one exception. That is, if you have a very strong first order phase transition, then there might be some third generation. That is, as I told you, the white dwarf is taken over by the neutron star, and in such a way, there might be some other other category of the star existing on top of this here. And this scenario is also very actively discussed by many people. This is called the third family scenario. The first family is a white dwarf, and this one is actually the neutron star. And then if you have a very strong first order phase transition, very, very dense and compact object might be possible depending on EOS. And in that case, so this one-to-one correspondence breaks down.
Okay. Any other question? Yeah.
On page 29.
29. Okay, here.
Yeah. So do I read correctly that the nicer data and this pulsar timing superior delay, they both give these very high mass neutron stars. Now, I see these the two solar masses.
Okay. You are talking about this region?
So that's just good confirmation that no one messed up. These are very different experiments, right?
Mm-hmm. Yeah.
Try to read that.
Yeah. So yes, but still, the uncertainty band is still not so small. So this is this is I think the 68%, and so the 95%. If you take the 2 sigma, then this is also really the big region. And so, well, about the the highest, the largest neutron star mass possible, then well, many people say many different things, but I'm very conservative. So some people say 2.5 or 2.6 might be possible, but I'm conservative. I would say that it is something around 2, twice over solar mass. That is a reasonable statement for the moment.
Just two questions. The first one, I think you mentioned for the Quark case or PQCD case, you mentioned your correction will come at order up I squared, right?
Yes.
But we know the trace anomaly for T mu proportional gate function. So you start at 1, but why? And you say, well, because the conformal symmetry, then the correction, PQCD correction starts at up I squared.
Because it's free, and then there's the scattering, and then there's the alpha S. So you have to go to 2 loop in the partition.
Yes. So this is PQCD calculation. So of course, if you include the gluon condensate, then maybe some. Okay, so I mean, if you extend this kind of, okay, this is just a standard PQCD, okay? So if you consider the gluon condensate, if you compute the gluon potential, then you may have some the scale anomaly, the gluon condensation, some scale violation. But anyway, that comes from the beta function. And then it appears from, anyway, the running coupling constant effect comes from the two loop, not one loop.
Because you're calculating partition function. So the zero photograph is the free circle. Then you insert one insertion that's a tree level, one level scattering, right? And that's alpha S.
Yeah, but then you said it starts from alpha S squared.
And now, yes, you want to get a running coupling, you have to put another loop in that.
I see.
Yes. yes. So yes, this is.
The power of alpha 3/3 the third half alpha.
Okay. That is some infrared the ring diagrams. Okay.
Second one is, I think it's 25 or 26. No, it's less than 26. Maybe it's for you. You have some more or less parametric estimate.
Parametric estimate of the mass here, like this. Okay.
So your energy, your kinetic energy is inversely proportional to R squared, but you also have, it's also proportional to A to the 2/3. Right? Then, I mean, you have kinetic energy, so like 1 R squared. But actually, because it's fermion, so actually you also have something proportional to the volume to the 2/3. So what I say is, if you convert everything into R, so your kinetic energy should be proportional to R to minus 1/3 or something.
Well, this one.
Oh, okay. So I'm thinking about
So this is a very simple argument. You see so here you see the P. Okay, the P is the energy because this is a relativistic limit, and then simply multiplied by the particle number. That's it.
Any other question?
Some of my friends have been in Sapiania and also they also make sophisticated calculations here by realizing, that you can create, you see, probably if you want to make, the neutrons start bigger and bigger, you have to put all the neutrons of top of the Fermi C. Fermi C grows up. Then at some point it pays to create, for example, a particle like lambda, sigma, or whatever. Because you don't have a Fermi C for that. So again, the system stabilizes and we carry also, a certain amount, a certain fraction of hyperons.
Yes.
So protons, and then there's a mixture of protons, hyperons, and electrons, of course, that's an avoid one.
So that is a very important point, and this is called hyperon puzzle. Hyperon puzzle actually means two different features. One is actually cooling problem, and another one is stability. And as I told you, some of the EOS are excluded, and they actually assume such kind of the significant hyperon components. But actually, there are many, interpretations about that. And some people try to introduce some three-body force, including the hyperons, and then from the phase space volume, such three-body interaction is expected to be enhanced, and then the hyperon could be suppressed, and also there are many lattice people also they compute the single potential energy, and anyway. So the statement is that actually the thousands of different ways to stabilize or to change the equation of a set, even with hyperons. So for example, one example is you can always introduce vector-vector reparative interaction, density-density reparative interaction. Then it is a piece of cake to fix the stable equation of state even with hyperons.
I'm asked to now it's just from my ego. The last slide that you have the perturbative QCD. I mean, what was for that?
Okay.
Perturbative QCD. I mean, the calculations. What do they calculate there?
Okay, so yeah, they calculated actually. Of course, so this is related to my I don't have to go to the, but anyway, I want to talk about some of the smooth connection to the PQCD regime. That is the valid description. Part of the QCD should be a valid description if the density is high enough. Yes, and then there are some the progresses. For the Koch mass, strange Koch mass, and also the next reading order.
That's already for Koch matter.
Yeah, Koch matter. Yes.
No longer neutron stars.
No. Deep inside of the neutron star, the Koch matter, the core is expected, and then that part should be given by PQCD calculation.
Right? I understand. Okay.
But there is actually a big uncertainty coming from the choice of this, some finite renormalization inside of this log summation. This is actually the big issue in theoretical uncertainty.
Okay. So you mentioned that by using this binary system, by using the subfield delay, we can measure the mass of the neutron star very precisely.
Yes.
But this only works for binary system. For some isolated neutron star, how do we have some good way to determine mass?
Well, that is actually the reason why this, this compilation of the data. This is actually some analysis from the X-ray spectra, but of course the atmosphere model and many things must be assumed. And of course, from the luminosity and observed the brightness, you can actually estimate some the mass limit. That is what was the name? I forgot. But anyway, some mass limit is also estimated from the brightness of the star. And but anyway, so that is just the Bayesian type inference is necessary, and so there are always a big uncertainty here. And so probably in the near future, the more promising direction is the gravitational wave signals. Then the chap mass, the total system mass, is very, very precisely determined. And probably each mass could be also identified with a very good accuracy. But this is again the binary system, not isolated.
Pulsars, right? Isn't that a single star? There's the pulsars.
Yes. This is yes. Yeah.
Okay. So yeah, if no question, let's thank Professor Shima and also Professor Huang for two very nice lectures this morning. And then we come back at 2 o'clock this afternoon.
Very nice lecture.